and for us it's kind of squeezed a bit, but okay, that's better.
How's that? Is that better?
Yeah.
Yeah.
Perfect.
Okay, I'll try to go quickly. So I'm going to talk about the PanDA Echo. I'm going to basically talk about Atlas and heterogeneous resources. So I'm going to start with this busy slide, which is the ecosystem for our workload management system, which also includes bits of data handling because the whole thing is mashed together. This comes from a slide that Alexei Klementov gave at the HEPEX workshop last October. Work gets into the system either by user submitting a task through a system we call JEDI, or into our Prodsys dev system, and production tasks come in this way. We use a database to keep track of metadata handling. Our distributed data management system is Rusio. This also interacts with our production system, and then interacts with PanDA, which is the work management system. PanDA itself talks to a process called Harvester, which I'll explain on the next slide. And Harvester then talks to our downstream resources, which are a mixture of clouds, HPCs, both in the US and in Europe. Atlas accesses HPCs in a couple of ways. For dedicated HPCs where we have an allocation and are grid-like, we either go through HD Condor CE and run a pilot on an HPC node, or we go through ARC and again run the pilot on a HPC compute node. We also have Harvester that runs on the edge of HPCs and allows us to do multi-node simultaneous scheduling and the like, and I'll get to that in a little bit. Harvester is a service that mediates the interaction between the resource and the workload data management system. It encapsulates the heterogeneity of all the systems we're running behind it, so that's nice. That'll help us going forward in the future, and it provides a uniform interface to the workload management and for monitoring. We use a plugin architecture to give us the resources, to give us the functionality needed for the resources that we're submitting against. As I mentioned previously, it can either be sitting on the edge of an HPC or just off it, or it can be sitting centrally and then launching through some sort of compute element. We also talk to K8s and the like. So it's experiment agnostic and has been used beyond just Atlas at ASGC. One of the things that we learned in using this whole system, and it has helped us for heterogeneous resources and ultimately will help us for GPUs, is fine-grained processing jumbo jobs. This is work that we've done over the past year and presented it at the last meeting at Adelaide. It's basically fine-grained simulation workflows. The idea is that we shape a simulation job to fit in the HPC workflow and then try to maximize using all the cores. What we've learned in doing this allows us to actually we'll be able to do more than just simulation for this, is the best way I want to say it. It allows us to sort of fit our work to an HPC batch system, which is important. Basically, the idea is we fine-grained processing. I'll just go through this slide very quickly, where we really want n nodes for T time. And typically, when running this, it was 250 nodes for 2 to 4 hours. And it gives us efficient processing. This slide just basically shows every time we're processing an event. The blue is waiting for event information. The green is actually running. The red is at the end of a running time where you just get cut off. The nice part of this fine-grained processing is in the fact that we handle it in our workflow management system means we can use these techniques for more than just simulation. This can be used for machine learning, especially since a lot of machine learning frameworks allow users to save after so many epochs and then pick up and continue on. And this allows us to more efficiently you can swap out GPU for CPU in that case. Or you can still obviously do machine learning on a many core CPU. PanDA had to make some changes, and to do that, it had to understand the fact that instead of having many little jobs come at once, it was going to have a whole block of work, and there would be some latency associated with that. On the bottom plot, it shows the blue line is PanDA making events available for a specific task. The red line shows essentially when things are done. So it shows the flats basically show when you're waiting for work to happen. In the queue of an HPC, suddenly you get the nodes. They run very quickly, a bunch of events processed, then you wait. And that's unfortunately what we see in a lot of these busy HPC systems, that you'll get a lot of resources, but you have to wait. Based on our previous successes, we've started to look at new workflows, whether they be active learning, which I'll explain on the next slide, or machine learning again. This is very useful for being able to make productive use of GPUs besides just reconstruction and the like, or intelligent data delivery service. This is important also in part of machine learning. And I'll explain to that in a couple slides. And in a farther future, we are investigating an Atlas Monte Carlo event generation, for example, MadGraph with GPUs, or as we saw a little bit yesterday, talk about Geant 4 with GPUs. That would help us for full simulation. Active learning is the ability to process some data based on some information, then make a decision, and then go through the next step of the process. Sort of, you can think about one example of active learning is if you're trying to do setting limits on a contour in a SUSY analysis. You don't want to simulate all the grid points. You'd really like to simulate around where the contour is, but you obviously don't know where the contour is a priori. This system makes use of our intelligent data delivery service to execute transformations, then talk to PanDA to be able to do the processing, and then the next tasks in the chain are sent back in. The IDDS is a general service which is being developed by some Atlas members, but also more than just Atlas members. It's an IRIS-HEP project in the US. And the idea is it's a general service to transform and deliver the needed data to the consumers. And the consumers obviously are the jobs running on the compute resources. It requires an orchestration of the workflow management system and distributed data management system into generalized workflows. As I said, it's experiment agnostic, and it's based on the abstraction and extraction of functions for orchestration. And it uses a plugin architecture for maintainability and extensibility. This allows us to do new workflows within Atlas, whether it be fine-grained tape carousel processing, active learning, hyperparameter tuning for machine learning, fine-grained data transformation, and the like. The first test of this system was to do data carousel, and the idea is that we wanted to be able to put data on tape that you would then reprocess at a later time. sort of what we're thinking to do for run 4. And the idea is that the PanDA, through a new component, would receive messages from IDDS and its ActiveMQ to take actions like update a file or task information, group things together, trigger job generation, and we've seen that it's been pretty successful in being able to orchestrate getting data from cold storage and to processing. Atlas has several GPU resources available to the grid. These are not necessarily HPC GPU resources, but essentially grid sites that have made GPUs available. They're all accessible via our PanDA system. Should point out that there's a variety of running time between 30 minutes to over a day. Right now, they're all NVIDIA GPUs. If you look at the GPU models, it's a wide variety of GPU models, and it's a wide variety of compute capability, as NVIDIA calls it, from their unit of 3.5 up to 7.5. So it's all over the map in terms of how powerful the GPUs are. Also, the GPU memory also varies. We have typically the consumer size, sort of 12 gigabytes of GPU memory, but we do have access to some much bigger V100s, which have 32 gigabytes of memory in the data center. In order to orchestrate this properly, of course, we've got to get this information out so we can make use of it, because you do not want to put work against the GPU where you need, let's say, 20 gig of GPU memory, yet you're only running on a GPU with 11 or 12. The opportunistic HPC resources also have GPUs. I'm just picking one machine as an example to orchestrate it. This is NERSC Cori GPU allocation. The next machine at NERSC, Perimeter, will have a GPU component and a CPU only component. The GPU part will be obviously the largest compute part of the machine in terms of compute power. Right now, we have a small allocation for testing and use on it, but what's important to point out here is that these systems have constraints in submitting to them, that these type of HPCs that are different from a typical grid HTC site. For example, here at NERSC, if you ask for only 2 nodes, then you have to have a job that runs relatively short. If you ask for more nodes, then you can run longer. It has an 8-hour cutoff in this system. The biggest machines that we have access to, Summit, has a much more complex table of number of concurrent nodes versus running time. The lowest configuration has a 2-hour limit, and if you ask for between 1 and 46 nodes, most of these big HPC centers also restrict the number of jobs that you have in their batch system. So this presents a wrinkle that we have to handle. Some of the challenges, as I pointed out early, the GPUs, though there's a wide variety of GPUs, as we heard yesterday, the ecosystem is quite varied with GPU, CPU combinations. As I said, the memory varies, the GPU power varies, and soon we will be dealing with multiple GPU vendors, as was pointed out yesterday, more than just NVIDIA, also Intel, AMD. Scheduling policy varies between HTC data centers and HPC data centers, so our workflow management system has to handle that. And we need better tools for monitoring GPU in situ, and also how well we're using the GPUs. That was talked about earlier today. And we should think more about whole node scheduling. And if we decide that we don't want to do too much whole node scheduling, then we have to ensure that the payloads are sufficiently isolated so that one processing using, if someone's using TensorFlow, they don't grab all the GPUs on a given node. So I'd like to conclude by saying in the past several years, Atlas has been developing WMFS tools and techniques to make good use of HPCs. And this information can also be applied to machine learning workflows on both the grid and HPCs. New tools and changes to PanDA will allow for a variety of new workflows, and a wide variety of GPU, CPU, and other accelerator combinations will require additional tools and monitoring for accurate brokerage of the work on these resources. And this is both going to be needed from the site side where they publish the information we can make use of, and then on the experiment side where we can actually make use of it. And that's all I have.